Hello everyone, welcome back to Physical Geology 1403. Lecture 4 today, continuing our discussion about igneous rocks and processes. We are learning about volcanoes and the hazards associated with them today. But before we jump into that subject, as usual, are there any questions or stories or interesting things that you want to talk about? Is the lab going to be a volcano? Unfortunately not. I wish, hold on a second. I wish that we were close enough to an actual volcano that I could take you. We have a bunch of dead volcanoes within 6 or 7 hours of us, but none that are interesting enough to be worth the trip. If you go to Big Bend, there's a lot of volcanic rock down there, but again, not really worth the trip, especially considering that since so many of you are miners, we would have to go through the whole transportation waiver system, and I would have to get a big bus, and to get a big bus, I need someone who has a CDL, and so there's a whole lot that goes into planning a trip like that, and at this point, there's not really anything volcanic that's close enough to be worth it. There was a question over here first. Yeah?
I'm so confused about cleavages. Like, are they just the amount of parallel sides on a mineral, or?
No, good question. Hold that thought, Jackson, okay? So, cleavage is the way that the mineral breaks based on its internal structure, okay? So, it sounds like you're kind of conflating the two ideas of crystal form and cleavage. Where crystal form is the original shape and those unbroken geometric sides, cleavage is when you get flat surfaces as a result of the breaking, okay? So, why does it make flat surfaces? Bless you. Anyone remember? Bless you again. Disrupting my class. Does anyone remember why cleavage planes form?
I forgot the word.
We learned about bonds holding atoms together, right? Are all bonds equally strong? No. So when I have a crystalline framework, a solid made out of a bunch of bonds, most of the time, they're not all going to be equally strong with each other. And so when I put stress on it, which ones break first? The weaker ones, exactly. And those make the cleavage planes that you see in a mineral. Why do they constantly repeat throughout that mineral? Because that mineral is just a repeating pattern of the same bonds all throughout its structure, which means that it's going to be weak in the same direction throughout the entire body of mineral. Okay? So that's what cleavage is. So when my mineral breaks and it makes these flat surfaces on the breakage planes, those are planes of cleavage. Okay?
So that means that if it breaks again, it will be like that again?
Yeah, if I took a hammer and I broke this, it would break into smaller pieces just like this, along those same planes. Okay? Does that help? Great. Jackson, you had a question? You don't remember, do you? It was the sneezing. It blasted the thoughts right out of your head. What did we say? When it was Cusque. It's okay. We don't need to say that to him. We don't need to say that. We like Jackson. Okay. Any other comments or questions?
Oh, are we going to make a volcano in here?
No. We are not going to make a volcano. I'm assuming you're talking about the plaster of Paris with red dye and baking soda and vinegar sort of thing we all did in grade school, right? No, we're not going to be doing that. That's a little messy and a little too kindergarten for our level. We are going to be learning about the theories of volcanoes, okay? We are not going to be building one, but I'm going to tell you how the real ones are made today. You're going to learn about that process, and it's cool. It's fascinating. Any other questions or comments? Any concerns with the class that you want to voice that I can help resolve? How are we feeling? Oh, yeah.
I have a question for the lab.
Yeah, that's fine.
There's 24 sets, right?
There are 24 samples in the set, yeah.
Where are the other 12?
I haven't handed them out to you. I wanted you to get your the grasp of sets of samples 1 through 12. And then when you're done with that, I will swap out that set with 13 through 24. You guys just let me know when you're ready for the second part of Lab 1, and I will bring those out to you. Okay? For my online students, you already have all of it in a single video that goes samples 1 through 24. You guys just let me know, and I'll swap them out. Okay? You will be getting Lab 2 assigned today. That doesn't necessarily mean you have to start it today. But today is when you're getting the last of the information you need to work on it. You got half of that information on our last lecture on Tuesday. You're getting the last half of that information today, so I'm assigning you the lab. But if you're still working on Lab 1, that's totally fine. Cool? Anything else? Yeah.
I wasn't here Tuesday. What was the third lecture about?
Igneous rocks and intrusive activity. So basically how we make magma and what it does underground, and when it cools off, what kind of rocks does it form. The lecture recording is on my YouTube channel, so if you go there, it should be up there right at the top of the videos list. It's the most recent video. And this one will go on top of it later today. Remember, my YouTube channel is Heart Rock Geology, or you can just follow one of the links of the labs that I've attached in each lab folder. Okay? Any other questions? Gosh, I love how many questions you guys are asking. What about cool stories? Anything relevant to today's subject you want to talk about? Yeah. Can you hold Diablo? Yeah, sure. You want me to pass him over there? Sure thing.
I know.
There you go.
Is Diablo a
Diablo is male. How do you think we can tell? The size? Females do tend to get a little bit larger than males, but that's something that's hard to tell until they're full grown.
The tail.
What about the tail? What about the tail?
I forget which one it is, but the thickness.
The thickness of the tail may be dependent on species, but you're right, there is something about the tail that is a good general rule of thumb.
And the scalage.
That's also more species dependent. I'm talking about a general rule of thumb for determining the difference between females and males. So there's this thing called sexual dimorphism, okay, in a species. That is a difference between males and females within the same species that allows you to tell them apart. In our species, it's often things like long hair. Females of our species tend to get longer hair faster than males of our species. That's one example of sexual dimorphism. So if I was an alien and I came to our planet, I wouldn't be able to tell the difference between a male and a female, except maybe by the length of hair. Which there are a few cases in our society which would confuse those aliens, right? Some women prefer shorter hair and some men prefer longer hair. But as a general rule of thumb, that's pretty much true. In the case of snakes, it's often the distance between the end of the tail and the cloaca. You guys know what a cloaca is? However you want. He just wraps around you. He thinks you're a tree right now, so he's just wrapped around you. Okay? I like wearing them around my neck because my neck is warm and snakes are cold-blooded, so he likes to just hang out there. You don't have to if you don't want to. He can't kill you.
Oh, man, in a minute.
You're what?
I said in a minute.
In a minute? I thought you said you would feed him an M&M. I'm like, that's not going to work, man. All right. The cloaca. Do you guys know what a cloaca is? A little biology lesson here. Do you know what a cloaca is? Cloaca. The cloaca is the one hole at the back end of a reptile. They only have one hole for their stuff. They use that one hole for peeing, pooping, and sex. It's the same hole for all of them. Okay? So, that's called a cloaca. And by the way, birds have the same thing. Birds have the same thing. Which is one reason why we know that birds and reptiles are related. Right? The same evolutionary object can't evolve twice. The statistical likelihood of that, ridiculously small. If you take 1404 from me, we discussed that sort of subject later on. But that's how we know that birds came from dinosaurs, which came from reptiles, which were the ancestors of Diablo. Okay? They all share that same trait along with others. Okay? So, but the distance between the end of the tail and the cloaca is often one way that we can tell a little bit of sexual dimorphism. So he is a male. It can be really hard to tell when they're just born, but I've had him long enough that it's for sure. Okay, I can breed him at this point. We usually wait until they're a few years old to breed them, and he's ready. So I may actually breed him with some of the snakes that my buddies upstairs have, and we'll see what comes out of it. But yeah. Any other questions?
You like choke a snake out?
Can you choke a snake out?
Yeah.
Yes, but that wouldn't be nice.
I'm not gonna do it. I was just like a question.
Theoretically, yes, you can. Well, it's not theoretical. You absolutely can.
Have you ever had any other kind of snake besides them?
Yes, the first snake that I ever had was a black rat snake, which, as the name implies, is black. But mine was an albino, which meant that it was white and pink. But its species was still black rat snake. It just had a recessive gene that manifested that caused it to have pale coloration. So I named him Paradox because he was an albino black rat snake. Yeah. Yeah.
When you got him, did you receive him like in an egg form or just like regular?
No, I got him 2 weeks after he was born. He was about that long.
Oh, dang.
Yeah, he was about that big. I bought him from the snake breeder, my buddy Chris over in town. He owns a business called Snakenstein Reptiles, if any of you are interested in snakes. He breeds them in his house. Yeah, I got him a few years ago, and he's about 2.5 years old now, and that's how big he's gotten. He'll get about 4 feet long when he's full grown. Give him about 4 to 6 more years. Yeah.
Did you train him not to bite, or why does he not bite?
No. So ball pythons typically aren't biters, unless they feel extremely threatened or they're hunting for food.
Oh.
Right? But you're not food. He's not going to bite you because he thinks you're food. He might bite you if you keep trying to grab his head, right? Or if you're squeezing him, right? Like you're trying to choke out a snake, he might try to bite you if he has the room to do so. But yeah, no, they are not typically biters, with the one exception of male pythons are pretty mellow. Female pythons are less mellow, right? They have a little less chill. So female pythons are more likely to take a snap at you if they're feeling irritable than male pythons are.
Question, but it's just a question. I'm not actually gonna go do it, maybe. But
You're asking a lot of sketchy hypotheticals here, brother.
so if you chop the head off, will it still move?
Yes, it will.
Yeah, it would. Yeah, that's reflex, that's electrical impulse going into the muscles still. Yeah, it would still move for a little bit. Yeah.
What other kind of animal do you think like is harmed by? Like if it like what does it not feel safe around?
What would a python not feel safe around? Anything that was obviously trying to hurt it.
So like what could the other animal be?
Anything with teeth. There are some species of snake that eat other snakes. There are birds that eat snakes. There are lots of things that eat snakes. Snakes are a yummy, delicious treat to just about anything that eats meat. As a matter of fact, I have eaten snake. Okay? I haven't eaten python. I've had rattlesnake. It's actually quite yummy. Okay? Yeah, anything that it feels is a threat to itself, it would defend itself against. For a ball python, they make ideal starter pets for owning snakes, because they are really chill. They've been bred to be that way. But also, their natural defensive impulse, if they feel threatened, is to curl up into a ball first and strike last. Other snakes, they will strike you first if they feel threatened, and then attempt to run away, right? Ball pythons, they like to curl up first, and then if they feel like their life is actually in danger, they will defend themselves by striking if they need to, okay? So as long as you're not being super irresponsible with Diablo, he will never ever hurt you.
Does it hurt, like, say you get bit, does it hurt pretty good?
He probably wouldn't be able to draw any blood. He's not large enough, and his teeth aren't big enough. Give him a couple more years and he might be able to, because python teeth are actually really small. They don't rely on teeth to kill their prey. Their teeth are literally only for that brief moment of latch onto rat long enough for body to wrap around. It's like lightning. It's like, and he's wrapped around it. They only need the teeth to hold onto the rat for that split second, long enough for their bodies to wrap around it, and then that rat's a goner. Okay? So their teeth don't fill any purpose other than anchoring the rat long enough to hold it down. Okay? Great questions. I have a geology thing for you, very relevant to today. Did you hear about the large earthquake that happened in Russia at the beginning of August, on August 3rd? It was an 8.8, largest earthquake we've seen in a while, in Kamchatka, which is this part of Russia that's across the strait from Alaska. Okay? That earthquake was so large that it actually set off the Krashenikov volcano, Krashenikov volcano over there, which is a very large volcano and has erupted in the past, but not in a long time. I think the last time it erupted was the 1600s. But it was such a powerful earthquake, it actually set off that volcano. And it's still spitting ash out. Still, yeah. It's been going for a few weeks. Very large earthquake set off a large volcanic eruption. Interesting. So we're going to talk about that process today. Are we ready to move on to our subject, or is there anything else you want to discuss? I'm happy to keep talking about things. Yeah.
I would like to talk about like where else has there been the biggest earthquake been?
The largest earthquake ever?
Yes, sir.
Shoot. All right. Well, we've had a couple big ones. Alaska has had some very, very large ones. Chile has very large ones often. The most recent large earthquake, the largest one in recent history, was the 2004 earthquake in Indonesia. It was the day after Christmas in 2004.
How big was it?
That one was a 9.6. I want to say it was a 9.6 or 9.7.
What's the highest it can go?
Well, hypothetically 10. We have a whole lecture coming up about earthquakes in Module 3, but the Richter scale that measures earthquake energy, or amplitude technically, goes up to 10. With each, a logarithmic scale, so each elevation upward is a factor of 10 in amplitude. So a Richter 2 is 10 times more amplitude than a Richter 1, and a Richter 3 is 100 times more amplitude than a Richter 1, and so on and so forth. So it gets very, 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 very powerful. I'll tell you more details about that earthquake towards the end of the semester, but it made a tsunami 33 feet tall. Yeah. Yeah.
What's the biggest one we've had?
Biggest one we've had here? I think the largest one we've had here is a 5.4. We don't get big ones here. We don't have any faults large enough to generate ones that big, that we know of anyway. And we also aren't close enough to a source of tectonic stress large enough or consistent enough to make the kind of buildup of stress necessary for that a much larger earthquake. Again, this is all stuff we'll talk about later in the semester, but a massive earthquake out here is extremely unlikely. I won't say impossible. As a scientist, I don't like saying things are impossible, because it's possible that it'll happen later on. Yeah?
Should we be worried that we're getting earthquakes now? Because before we didn't get them.
Oh, we did get them before.
Oh, we did?
Oh, yeah. Yeah. It's not like we started earthquakes, guys. Humanity does not have the ability to do something like generate a fault line that earthquakes occur along. Earthquakes happen because of a buildup of stress along a crack in the earth that we call a fault. Okay? We don't make those cracks in the earth, and we can't make the stress that builds up on them. That's tectonics. That's well beyond our ability. That's Mother Nature. That's Earth doing its thing. The only reason why we are experiencing more earthquakes now than people can recall in history is because our oil-filled operations do a lot of stuff underground. We poke our straws down there. We introduce fluids into the system. We store water underground. We're pulling oil out. We are affecting the underground system, which is going to have some effects. And it looks like some of the effects are setting off some of these earthquakes. Now, here's the thing. Earthquake energy releases and then immediately starts building again. Because just because you have an earthquake doesn't mean that the source of that built-up stress is gone. You relieve the stress, and then it immediately starts building up again to be released a few hundred years later, normally. What we are doing with our operations here is simply causing that stress to be released early. If I accidentally introduce a little bit of water to a fault line, it might cause that fault line to slip, and I get an earthquake. It would have gone off 100 years later anyway, and guess what? It would have been more powerful too, right? So maybe that 5.3 we had a few years ago could have been a 5.7 or a 5.8 later on. I can't guarantee that. But what I can guarantee is we do not cause the buildup or the physics behind earthquakes. All we have been doing, it appears, is causing the earthquakes to occur earlier than they normally would. right? Does that make sense? Can you discern the difference between that? Good. Any other questions? What a great discussion to have before our lecture. I love it. If we could do this every time, that'd be awesome. All right, shall we jump in? Great. Let's talk about volcanoes. I'm going to introduce you to my friend. This is Helen. Mount St. Helens, technically, is the name, okay? Mount St. Helens erupted on May 18th, 1980. Way before any of you were born. It was actually way before I was born, too. I know, so old, right? Ancient, practically, okay? This occurred 45 years ago, okay? Earlier this year was the 45-year anniversary. So Mount St. Helens, for a long time, people knew that there was a potential to erupt. But leading up to this day, it started manifesting some changes. There were some things that they were observing about Mount St. Helens that caused them to think, ooh, it might erupt soon. When I say them, what am I talking about? There is a whole government agency called the U.S. Geological Survey, or USGS, that their job is monitoring geological events, threats, and resources in the United States. So water resources, mining resources, volcanic activity, earthquakes, landslides, all of that. There are different departments within the USGS that are in charge of monitoring these things and regulating them as needs be, okay? So they were monitoring this volcano, and they sent a geologist out there to basically sit and babysit the volcano and watch it. They put out an alert telling people, hey, we think this volcano is going to erupt soon. You should vacate the area. Now, how many of you think that if I told you right now, hey, as a geologist, I am warning you, there is going to be some big disaster here and you need to take your family and leave, how many of you would leave today? Chris would, but she knows where I'm going with this.
Oh, yeah, I don't know.
You'd be gone already? Like as soon as I said you need to leave, you would just, like the road runner out of my classroom. Yeah? That's good for you. A lot of people have a hard time with that. If you need another case study of this, look at New Orleans and Hurricane Katrina. Right? Oof. A lot of people died. Why? Because they didn't leave when they were told to. A lot of people, and it's not always just obstinance, by the way. Some of it is just like, it's cultural. I cannot imagine leaving this place. I spent my life here. My parents grew up here. My grandparents lived here. My great-grandparents built this house, right? Whatever it is, a lot of people cannot imagine leaving where they live for any reason. And unfortunately, when this volcano did erupt, it killed 59 people. 58 of those people were residents of the area. The 59th was the USGS geologist that had the misfortune of setting up his camp in the wrong place. The day before the volcano erupted, on his hillside that he was watching the volcano from, he was using a laser to measure it. He measured that the side of the volcano expanded outward 6 feet before that last day that last moment that it erupted. The volcano was expanding because it was filling with lava. Or at this point, magma, right? It was getting ready to pop. I'll talk more about how we can determine when a volcano is going to erupt a little bit later on. But he measured this movement, and he was calling in, he was making regular reports to the USGS headquarters. The last thing anyone ever heard from him was, control, it's happening. He had set up his camp on this hillside. Now, looking at this after picture of the volcano, which direction does it look like it blew up in? Out the side. This is very untypical. This is not typical. Okay? It's atypical, not untypical. It is atypical, okay? For volcanoes, they will usually erupt out the top. Or maybe off at a very slight angle, but blasting out the side like that, not normal. And unfortunately, Mr. Johnson, who was the geologist there, had pitched his campsite over here. That was the last message anyone ever heard from him. We only just found his trailer buried in mud from the eruption a few years ago. Yeah. So these were the 59 people that were killed. And it was this massive country-affecting event. Well, why? Only a few people, 59 of them in the immediate area, died because of the event. But the ash went 18 kilometers into the atmosphere. It went real high. And the winds that high carried it all over the place. Okay? I actually have some Mount St. Helens ash right here. I didn't get it. This was collected right here. Someone collected this when it fell here. Yeah.
Wait, where is that at?
Where is Mount St. Helens? Mount St. Helens is in Washington. So the ash went as far as Oklahoma, by the way. Yeah, what? You may. Yeah, sorry. Okay, so I'm going to hand this out. This is Mount St. Helens ash.
That's real.
It's real. Yeah. 1980,
How long ago did they get that?
when it fell.
Oh,
Yeah, you can't walk out in your backyard and find it anymore, right? It's been incorporated into the soil. But yeah, that is ash that fell. How far away are we from Washington? Oh, very far.
pretty far.
Yeah, very far. Huh? I didn't pay for it. It was in the collection here when I started working. I don't know who collected it, but it was here. It's not like it's worth much. The ash fell literally everywhere between the volcano and here. Like you can go to, I've been to so many houses over on the West Coast where people just have a jar of ash on their mantelpiece above the fireplace. Yeah. And they'll tell you, yeah, this is from the Helens eruption. My grandfather collected it. Yeah. Okay, so this eruption had the energy equivalent of 1,600 bombs that were dropped on Japan. Specifically the one on Hiroshima, the big one. Okay? That's a lot of energy. All expended in a big, right? And it blasts millions of tons of rock and debris out from this eruption. Okay? So volcanoes are really not something that you mess around with. By the way, someone tell me what the differences between the before and after are here. Let's start.
Wider.
It's wider? What do you mean?
You know, like it's like
It's not as tall.
The volcano's not as tall? Right. It actually lost about 400 meters off the top.
I think a 1 yard over.
What else? The bottom looks more wide here or wide here? Here? In the after? Yeah. What's missing from down here that's not there? Trees. Look at all of the dense forest. This forest is so dense that you can't even see the foothills, right? Every single tree blasted to smithereens in this eruption, leaving it a bare landscape in the after picture. There are so many trees you can't even see the reflection of the volcano in the water. And now all the trees are gone, so the image of the volcano is present in the water here.
Is it still like that today?
No, after 45 years, the forests have started growing back. It's not nearly as lush as it was here, but it's more than this picture. The after is a lot what? Darker? Oh, that's just the difference between the filters that we're telling the sky colors. But yeah, I see what you're talking about. You're right, that is a difference. Okay. I'm going to show you another volcano. This is Mount Tambora. Mount Tambora in Indonesia. Mount Tambora is what we call a supervolcano. Have you ever heard that term before? Usually you hear the term supervolcano in relation to what?
Somebody's anger.
Somebody's anger? Man, don't get Juliet mad. She turns into a super volcano. You know what I'm talking about? Right now. I'm just picking on you, right? Okay? I've never heard that as a term before, but that's good to know. No, a super volcano is exactly what it sounds like. A massive volcano, way larger than the rest of them. Mount Tambora is one of 2 supervolcanoes on our planet. Do you know what the other one is? Yellowstone. Yellowstone and Mount Tambora are the 2 active supervolcanoes. Okay? Now I say active for a reason. There are actually 26 supervolcanoes scattered around our planet. The other 24 are dead, no longer functioning, no longer potential to erupt. These 2, Yellowstone and Tambora, are the only 2 that can erupt. They are still alive, so to speak. Yeah, Mount Tambora erupted in 1815. And it sent ash over the entire planet. When Mount Tambora erupted, it caused an early winter that killed crops in the eastern United States on the other side of the world. It caused a small famine in the United States because so many crops died before they could be harvested. So volcanoes obviously are not only a concern for the local inhabitants. The smaller ones, I say smaller as a, it's just a relative scale, right? Like Mount St. Helens maybe affect a region and kill people locally. Supervolcanoes have the ability to affect an entire planet. Yellowstone. We're going to talk about Yellowstone today. Let me touch on it for just a moment. You ever seen a headline, a news headline, one of those sensational news headlines? It's like, Yellowstone due to erupt any day or anything like that? Man, what kind of news sites do y'all hang out on where they're not trying to scare you with Yellowstone eruption news? Okay? It comes up all the time. Scientist says Yellowstone due for eruption. Yellowstone will kill us all. Something like that. They're not entirely wrong, but they also aren't getting their facts right. Okay? When a volcano or any other geological event is due, what they're talking about is averages. Okay? Someone describe to me what an average is. The mathematical concept of an average.
Like your 2.0 average for grades.
Okay, so that's an example of one, but what is an average? Do you know how to find an average? How do you find an average?
You add everything together and then divide it by the number of how many items.
Exactly, that's it exactly. You have multiple data points, you add the value of those data points together, and then divide that value by the number of data points you had. And what this gives you is a number we call the average, which we kind of treat as the
Median.
Yes, exactly. The median, okay? So here's the mistake people make, including people in the news, because they're not concerned about the facts. They're concerned about what people will read. They see Yellowstone erupted 750,000 years ago, and it erupts on average every 600,000 years. You know what that means to them? We're 150,000 years due for an eruption. But that's not how nature works. If I said that a volcano has erupted twice in the last 10 million years, okay, then that would mean it erupts on average every 5 million years to someone who doesn't know any better. But to you and me, we do know better. It could erupt 1 million years ago and then 9 million years before that. It could erupt tomorrow. It could erupt in another 20 million years. Nature doesn't care about averages. Only humans do. So when you see those sensational news headlines, Yellowstone due to erupt, it doesn't mean squat. Okay? Now, let me put this little statement out there. It very well could erupt tomorrow. We watch Yellowstone very closely. But it could erupt in a million years too. Okay? If Yellowstone, we watch it closely because if it did erupt, it would essentially destroy the United States. The nation as a whole would no longer be what it is. It would kill a bunch of people in the middle of the country and then effectively slice the United States in half down the middle because of all of the, I'm talking dozens of feet of ash that it would put down. Okay? So you'd have to evacuate all those 4 states that Yellowstone is right in the middle of. And then everyone would flock to the East Coast or to the West Coast to escape from the ash. And everywhere in the middle of the U.S. would basically be uninhabitable for a long time.
So we would be screwed.
We would be a very different nation. I would like to think we still remained one nation, but it would be difficult when you cannot drive or fly from one side to the other. Don't know. Hypothetical at this point, but it would not be good. And there would be ash falling all over the planet, by the way. There's ash from the last Yellowstone eruption in Europe, in South America. It just wouldn't be as bad as it would be here.
Like it's still falling? Or?
Oh, no. There are deposits of ash from that last eruption 750,000 years ago and change. You can dig down through the soil until you find that layer of ash from the last eruption. That's actually one of the ways that we help determine, we call those marker beds. This is something that comes up later. A marker bed is something that you can find anywhere around the planet, like the layer of debris that was deposited from the asteroid that killed the dinosaurs.
So kinda
That's
like
present everywhere too. Huh?
Kind of like sediments, kind of?
Yeah, it's essentially fits there between a layer of sediment. Okay? And we can find that marker bed over most of the planet. Yes. Okay. So, volcanic eruptions. You got a couple of different flavors of these. Okay? You've got your explosive eruptions, like this. Okay? And you've got your tamer sort of just kind of spitting lava out eruptions, more like this. This is more of like what you would find in Hawaii. Okay? Before I tell you why, does anyone want to take a stab at why there are 2 different types of eruptions and what can determine what kind of eruption you get?
Their location and kind of rockets they have.
Ooh, their location. And what kind of rock do they have? Or what kind of...
Shape?
Because it's not rock yet.
Magma.
Magma! Here we go! Nice! Let's explore this a little bit. What are the differences between magma that could determine the explosivity of your eruption?
The minerals that make up the magma?
The composition is what you're going for. And yes, absolutely. What was over here? Yeah, the properties, the characteristics of that. What about the composition would determine explosivity?
The reaction of the composition might be like more like it could be like more exposed to like explosions or
No, there's not an external factor, okay, that's going to influence this. Let's talk about it. It's the viscosity. It's the viscosity of the magma. What is viscosity? Remind me again.
The thickness.
Like how it flows.
How well it flows. Thickness. Resistivity to flow. Resistance to flow is viscosity. You remember my water and my corn syrup? I'll flip it over again, right? Water and corn syrup. Which one was more viscous? The corn syrup. Yeah. More viscous, less easy to flow. Less viscous, more easy to flow. Oh, it's going. There it is. Got a big old goop of it. Okay? Do you remember what composition it was that was tied to? There's a big old bubble forming in there. That was tied to viscosity. What was the characteristic of magma? The composition of magma that was tied to high viscosity properties. What was it? Yeah. Silicates are the minerals that form. Are you talking about silica? Silicate is a classification of mineral. Silica is the silicon-oxygen compound, okay, that forms in your lava or magma. Okay, is that what you're talking about? Okay, silicon is the element. Silica is the combination of oxygen and silicon that forms in your magmas. And silicates are the minerals that form around that. Okay, so you're right, Gavin. It is the silica content. The more silica it has, is it more viscous or less viscous?
More viscous.
More viscous, harder to flow. So it is the silica content. Temperature also plays a role. The hotter it is, the less silica bonds form, and therefore it will still stay runny for a while. But as it starts to cool off, if it contains more silica, it will get gummier. It'll get more viscous faster. Okay? And then there's the volatiles. What are volatiles? Gases. The gases that are forming inside of that. Take a look at these videos. In this top video, we got corn syrup. In this bottom video, we got water. Is there a similarity? They both have bubbles. There's gases in both. But what's the difference?
One's escape
One's
faster.
faster and one's slower.
In the less viscous water, the bubbles can escape upward and make it into the atmosphere. In the more viscous corn syrup, what are the bubbles doing?
Stay in there.
They stay in there, my friends.
So it blows up pressure, and that's what makes it rises up and explodes.
Boom! Literally, right? Okay. This is what causes a volcanic eruption. Gases form in my magma as it is cooling down, approaching the surface. As the gases form, pressure builds inside the chamber. The more viscous lava does not let that pressure escape. The bubbles can't go anywhere. The less viscous lava lets the bubbles escape. When you have more viscous magma, bigger, boomier eruption. Less viscous magma, less big, more of a spitty sort of eruption. Yeah.
Why on some volcanoes like ash comes out first?
We talk about ash here in a little bit, okay? We'll get there. Okay, so here we go. Why do eruptions happen? Let's go start at the beginning and work our way up, okay? Here we have the intersection of the lower mantle, the asthenosphere, okay, where it's, yeah, you may, okay, where it is that, what term did I use? Squishy, okay, Play-Doh-y sort of texture mantle, too hot to be solid, too pressurized to be liquid, so it's somewhere in the middle. Still kind of qualifies as a solid because it's not a liquid, but it's very moldable by the pressure. Okay, so we get a lot of that here, and it starts making its way up through the lithosphere, the harder, rigid mantle. As it gets upward and decreases in pressure but keeps that temperature, it enters a melted state. Okay, so we get blobs of magma making their way up here, cutting through the upper mantle. They pool underneath of the crust. Then they start chewing their way up through the crust until you end up with a magma chamber just underneath the crust and a tube, a conduit, from the magma chamber to the surface. That's going to make your volcano. And what kind of eruption do you get? It depends on the type of magma you got. Okay? Now, watch this little video here. Tell me what happens as this guy pops the cork out of this carbonated beverage. Yes, you may. Okay? He's going to pop a cork off of this carbonated beverage, which in my college class we are going to call a root beer. Okay? This is clearly a root beer. All right? Watch what happens. Cork pops. What was the first thing that came out? There was a puff of gas, and now what's coming out? Yeah, the super aerated, bubbly fluid from inside. As more gases escape, the less aerated it gets. And so you're going to see this fountain kind of drop back down as more gases escape. And what comes up is less bubbly, less aerated, until what's oozing out is just the fluid itself. Okay? Getting pushed up and out. Okay? We've all had an experience like this. You're driving home with your soda. go over a speed bump, forget you have soda so you didn't slow down, get home, pop open the soda, you've lived this same experience that a volcano goes through. Okay? It's the same concept. So let's see a volcanic eruption. I'll show you that in a second, actually. So you've got your calm style eruptions, and I know that doesn't look totally calm. We call this a lava fountain. This is about as violent as volcanic eruptions in Hawaii get. Okay, maybe a 50, 60 fountain of lava. It's about as bad as it gets. It's not typically a sort of thing from that kind of volcano. We'll talk about that kind of volcano in a little bit. Okay, and then this is more of your, 1,500 nuclear bomb style energy eruptions right here, explosive type. Okay, so your more felsic, viscous magmas will make an explosive eruption, and your more mafic, less viscous magmas will cause a less violent eruption, calm-ish eruption, I call it. Okay, so let's see a video of an actual eruption. This is Mount Fagradalsfjall in Iceland. This erupted 2 years ago. Maybe it was just last year, actually. It's not that far from the capital of Reykjavik in Iceland. This guy flew his drone over it. This was the only drone to survive with its footage. People flew dozens of drones over this erupting volcano. Look how close it got to that lava. All the other drones flew into a piece of lava and then got destroyed and fell down into the volcano. This guy's drone footage survived. Fantastic photographer, by the way. Follow him on Twitter. His name is Bjorn Steinbeck. So fantastic footage there. But yeah, so that was those actual footage of an eruption, and you could tell it wasn't very explosive. There was some stuff flying up, but it wasn't, massive clouds of ash everywhere. That was more of your calm-ish style of eruption. Okay? Now, of all the material that gets pushed out to Earth's surface, all the lava that gets pushed out to the surface, 90% of it is mafic, 9% of it is intermediate, and 1% of it is felsic. Why? Why do we have so much mafic material that gets pushed out to the surface? Anik, what do you think? Take your shot. Throw a dart at the board. If everyone throws a dart, someone will hit a bullseye, right?
Produce more in the volcano?
Ooh, not produce more in the volcano. Give me a second. I want to pursue this with Anik. Oh, yes. Yes, you may. Okay. Could you leave the snake in here, though? Yeah, okay. Okay, so it's not that it's produced more in the volcano. Let's stick with that first part of the statement. Produced more. He's right. There's more mafic material produced at the surface. That makes it to the surface. But why? Remind me of your name, brother. Remind me of your name.
Carlos?
Carlos?
Yes, sir.
Carlos, what do you think? Why is there more mafic material produced at the surface, pushed up to the surface, than intermediate or felsic? I think Aaliyah has a thought here, and I want to let her have it. Yeah, you're describing a part of the process correctly. But that part of the process is true regardless of the type of magma. What I'm specifically asking is why mafic more than the rest? Any ideas there? Stronger bonds? We're not going to dive into the strength of the bonds within a magma right now. Okay? Keep thinking. Let's see if, what do you think?
It cools off on the surface. Maybe?
What cools off on the surface?
The magma.
All of it does, right? But why would that make a difference for the type of composition? Huh? What about iron?
It cools quicker, so the top layer.
No, you're right. It has something to do. Iron plays a role in this, specifically the ratio of iron to magnesium, which is that higher in mafic? Yes. Okay, so we have mafic that is higher in a ratio of iron to magnesium, which means it is what? What were you going to share? You don't have to answer that specific question.
I was going to ask if the width flow to the top faster because it's less dense.
Ah, there it is. And that actually does answer my question. He says it will flow faster. Why will it flow faster? Because mafic is less viscous is the word I'm looking for. Okay? It is less viscous, which means it flows faster. If it flows faster, more of it gets out of the volcano or vent or wherever it's coming from before it cools off. It's like, what's a good example of this? Imagine if I had a squirt gun filled with water, as they typically are, right? I got a large bore squirt gun. It's filled with water. A lot of water comes out of it, right? What happens if I fill that squirt gun with mud?
Nothing.
How much is going to come out of it? Not much. Maybe a little dribble before it gets clogged. That's what's happening here. Mafic magma and lava, being less viscous, can flow out faster and make room for the lava that's coming behind it. Whereas intermediate is a little thicker, a little more viscous, less of it gets out before it all cools off. And with felsic, hardly any of it gets out at all. Which is why the more explosive type volcanoes that have felsic magma as their source of energy, of that pressure buildup, don't usually have lava flows associated with them. You get the big explosion, but not usually a lava flow. It can't make it that far out of the volcano. Does that make sense? Now, the fastest lava flows can go up to 30 kilometers an hour. I think I mentioned this last time. You better have wheels because you're not outrunning that. Can any of you run 30 kilometers in an hour? You can, Jackson? Do you run track and field? Then how do you know? He's just that confident. Yeah. I bet I could outrun a lava flow. You should use that line. You should use that line. That's a good line. Next time you need a date, use that line. Okay? It's like, what was that dumb thing that was going around earlier this year? Who would win? Like 100 dudes or a gorilla? Wasn't that a thing?
Yeah.
It's like, who would win? Jackson or a lava flow? The lava flow would win, brother. I'm sorry. You get within 20 feet of that lava flow and it lights you on fire. You're done. Yeah, man. We're talking about like lava that's between 400 and 700 degrees Celsius. You get within 20 feet of that, you're going to light on fire. You'll probably collapse from heat exhaustion before you're even within 20 feet. Which is, okay, have you guys seen the second Jurassic World movie? Okay, you know where Chris Pratt's tied to the log? Or he's like tied up and he's on the other side of the log because he's paralyzed. And the lava's like flowing a few inches on each side of him. And it's like, I'm sorry, bro, you've been dead for 10 minutes. It's like, before it even got anywhere near you, you'd be on fire. I have a hard time watching movies like that. Not nearly as hard a time as the people that watch it with me, though. Okay. All right, we good here? Any questions so far? No? Good. Then let's learn some Hawaiian. Hooray! All right. The first Hawaiian word you're going to learn is a'a. Say it with me. A'a. A'a. This, yeah.
Kind of off topic. Did they have a tsunami?
What?
Did they have like a tsunami?
Who?
Hawaii?
Yeah, because of that big earthquake in Russia. Yeah, that 8.8 earthquake we talked about generated a tsunami. It went across the Pacific. Yeah. Yeah, it generated a tsunami. It went across the Pacific. It was only a few feet high by the time it hit Hawaii, though. It didn't make any damage. It did A little bit of damage in Alaska. I think there was maybe one instance of damage at a port in California. It did a lot more damage in Russia. It was an 8-foot tsunami in Russia. It ended up only being like 3.5 feet by the time it hit Hawaii and the rest of the US, though. Yeah. And by the time it hit Australia, I don't even think that they noticed it. Right? Okay. This is Say it again. Good. Okay. Why do we call this particular lava rock Well, if you're a barefoot Hawaiian and you're walking on this, what are you going to say? I love that joke. That's not actually why. Okay? That's just the name that they gave it. Okay? So this is lava rock. Okay? This is an igneous rock. This is actually the igneous rock basalt. You have seen it before. It's just highly vesicular and cooled off at the surface. This is from a lava flow. Okay? So this is rough, jagged, blocky, chunky basalt flow rock. Okay? And we give it the Hawaiian name because it was first studied and characterized by scientists in Hawaii. And so they usually, scientists, if they're considerate, will typically use the words of the indigenous population of the area that they do that in. Okay? So this is lava rock. So that's what happens if you have a mafic lava flow that cools off quickly at the surface. Okay? It's a low temperature flow. It's a low temperature flow, okay? When you have a high temperature lava flow at the surface, it tends to run faster, which means that when it does cool off, it's going to have more of a smoother, sort of ropier, kind of wavy texture to it, not that rough, chunky texture, okay? This is called pahoehoe. Say it. Pahoehoe. Thank you for jumping the gun there, okay? Pahoehoe. Good. Okay. So same thing as that but different appearance. Same composition. As a matter of fact, this may have come from the same flow, just at different places. The high temperature flow closer to the source would have formed pahoehoe. Like you see there, that smooth, ropey texture you see forming on the top of that flow, that's going to be pahoehoe. But if that flow keeps making it further and further and further away from the source, it starts to cool off. It becomes a low temperature flow. It's going to cool off and form chunks, blocks, like that. Okay? So this is what mafic magma, or excuse me, at this point it's lava because it's above the surface, right? Mafic lava is going to form these two types of lava rock at the surface. Yeah, of course. Okay. A few other things that we can find associated with volcanoes and their eruptions. Lava tubes. Have any of you ever been to Hawaii? Okay. Highly recommend to visit. I lived there for 3 years, and it got a little old after the first year because you're stuck on an island and you've done everything 5 or 6 times. At that point, going back to the mainland US feels like a vacation, right? So I would highly recommend visiting Hawaii, but I don't know that I would necessarily recommend living there, okay? But it has fantastic geology, especially if you're interested in volcanoes, which I really was while I was there, okay? So, but they've got tons of lava tubes that you can actually go and walk through. What is a lava tube? Well, imagine that you have a high temperature lava flow, okay? And it's just kind of, it's going along the ground. Maybe it finds a riverbed and it's flowing through the riverbed. But on the surface, on the outer edges, it starts to cool off. And it makes a nice, ropey, thick, smooth tunnel. Pahoehoe tunnel, okay? With a smooth texture. It essentially makes a shell around itself that still has lava traveling through the middle, going downhill. But as time goes on and our eruption starts to cool off, that lava that's flowing through that tunnel starts to cool off. And instead of forming pahoehoe, it's ultimately going to form, what's the low temperature version? Good. It's going to make an deposit there, okay? It's going to cool off into chunky blocks, okay? Broken up chunks. Now, the next time that volcano is gearing up for an eruption, what's the first thing that comes out when you pop the cork? Gas. That burst of gas is going to go down the paths that the last eruption opened, and it's going to encounter this tunnel, which is filled with a bunch of chunks, and it's going to shotgun blast those chunks out the other side of the tunnel. And all of a sudden, you've got an empty lava tube. Now, assuming it doesn't get filled with lava again, it stays an empty lava tube. Okay, and that's what you can go and take tours through if you ever go to Hawaii Volcano National Park. Highly recommend. Super cool experience.
If they just start filling up while you're in there.
You would know if the volcano is going to erupt. And if it was currently erupting, they don't let anyone near it. Right? Anytime that there's a volcanic eruption, they shut down that part of the park. Okay. Okay. A block lava is what you get when an intermediate or felsic lava flow actually makes it to the surface and goes some distance. As that intermediate and felsic lava starts to cool off and mineralize and crystallize and solidify, it's going to break apart into these blocks. It's not going to make a nice flat flow like a basalt would. Think of it as the same concept. Think of it as the same concept as drying mud. If I filled a cookie sheet with mud and then put that cookie sheet in the oven and dried that mud off, what's it going to look like when I bring it back out? It's going to crack.
It's going to look like a brownie.
Yeah, it's going to be a delicious brownie, right? No. It's going to have cracked all the way through it. Why? Because as I'm drying it out, I am removing water and changing the overall composition of my substance. And as that water leaves, everything else kind of constricts, kind of comes closer together because there's no water taking up all that space that it used to. And so you get cracked mud. The same thing is true here. As it solidifies, it shrinks, becomes more dense because it no longer has the same amount of energy, and they crack apart from each other, and your intermediate or felsic flow turns into essentially a field of broken blocks. Okay? Then we've got pillow lava, which is another cool phenomenon. This is what happens when you get lava that's flowing underwater. The outer surface of your flow is cooling, quenching immediately, making that glass, right? Or very, very, very fine-grained rock. Okay? But the lava is still pushing through that tube. And so the front is constantly moving outward, cooling off instantly, and then moving aside for new stuff to come behind it. We call this pillow lava. Check this out. Yeah, the front is always moving outward. New lava constantly cracking the front and pushing out in front and cooling off immediately and getting cracked and pushed aside.
So it's like a big old tube.
It's like a what? A tube? It's not what I thought you said, but yes. Okay. All right, so let's go back to what we talked about earlier, the gases. The explosivity, it comes down to the gases. Well, what are the gases that we get in magma? So depending on the composition of my magma, I can have anywhere from 1 to 6% of that magma being dissolved volatiles. Those are gases that are just waiting for the right conditions. A little bit of cool off, a little bit of a drop in temperature before they can actually form into the gas bubbles in the mixture. Okay? Most of that is water, by the way. The vast majority of gases that come out of a volcanic eruption is going to be water. 70% of all the gases that you see from an eruption is water. Then you've got CO2, and nitrogen, sulfur dioxide. Every volcanic eruption typically will put out thousands of tons of this stuff every day. Okay? That's a lot of gases entering the atmosphere. As a matter of fact, this is what made our atmosphere. Billions of years of volcanic eruptions on our planet are what made our atmosphere. Look at this mixture. Water, CO2, nitrogen, sulfur dioxide. This is essentially all the ingredients in our atmosphere today. Do you know what our atmosphere is mostly made out of? What's the biggest ingredient in our atmosphere?
CO2.
I hear CO2, oxygen. What's the biggest ingredient? Is it CO2 or oxygen? Huh? What? It's nitrogen, my friends. Most of the gases that we breathe are nitrogen. We simply rely on the oxygen compound. Okay, the oxygen component, excuse me. Okay? There's a lot of CO2 and methane and other argon and other gases out there, but we separate the oxygen from all that stuff and use it in our blood. But yeah, a lot of it is nitrogen. So as billions of years of volcanic eruptions pumped all of these gases into the atmosphere, the water would fall down and form oceans. The CO2 and sulfur dioxide would build up and build up and build up until eventually we get this interesting new thing called bacteria. This living thing that pulls sulfur dioxides in some species case, methanes in other species case, carbon dioxide in other species case, and uses photosynthesis to crack those things apart. Separate the sulfur from the oxygen. Eat the sulfur, expel the oxygen, I don't need it. And little by little, year after year, millions after millions after millions, and then eventually billions of years later, we have an oxygen-rich atmosphere that can support life like ours. Yeah, sure. Okay? But the gases, they came from volcanoes. We have an atmosphere because of the volcanic process. Okay. Pyroclastic material. I told you last time about a texture, an igneous texture called pyroclastic texture. I told you it is the only igneous texture that does not come from magma or lava. It is caused from a volcanic eruption. So now let's talk about that. Okay? So pyro means fire, clastic means fragment. It comes from a volcano, okay? From the eruption of a volcano. Now there's a gradient to the size of things that can come from this. And you can have things as small as this ash, microscopic, okay? This can make pyroclastic rock. You can make, say, a tuff. Where's my tuff? There it is. This is a piece of tuff, Tuff, right? You remember that rock that's made from a welded ash? If this ash had fallen while it was still super hot, it would have welded itself together and made a tuff. And it did, just closer to the volcano. The ash that fell out here was already so cooled off that it wouldn't be able to do that. Okay? So then you've got lapilli, which are your little cinders, the tiny little fragments, the bits and pieces that are falling from the volcanic eruption. We call those, generally we would call those cinders, okay, or lapilli. And then you've got bombs. I mentioned this to you last time. So this is a bomb. This is a lava bomb. This is a chunk of semi-melted volcanic material that got blasted through the atmosphere, could have flown miles before it finally landed. But because it was in a semi-melted state, my camera stopped following me there. Because it was in a semi-melted state while it was flying through the atmosphere, it formed an aerodynamic shape as it flew through the atmosphere, like a raindrop does. Where does the raindrop shape come from? Raindrops don't take that shape just because. It's an aerodynamic shape. The water forms that shape as it slips through our atmosphere because it's the most efficient shape for that water to travel in. Physics, it's wonderful. Semi-melted rock does the same thing as it's flying through the atmosphere at 100 miles an hour. And so that's why it took on this interesting aerodynamic shape here. That's a lava bomb. I'll pass that around. Huh?
I said that would have sucked to get like flying through the air and you get hit by it.
Get nailed by a lava bomb? Yeah, that would suck. Be the worst day ever. Last day ever. Okay. Some other products that come out of a volcanic eruption, which we saw last time. This is pumice. You remember our friend pumice? Floats on water, right? You use it to scrape dead skin off of your feet. Go to a spa and they hand you a bar of the stuff, right? Well, pumice is what you get. This is the foam. You get that initial burst of gas out of your volcano when you pop the cork, and then that foam that comes out, super aerated material. If my material is rich in silica, aka felsic, you're going to get pumice. That's your foam. Comes out, instantly cools off in the atmosphere or in the water if there's any nearby, makes this hole-filled chunk of glass. What if it's a mafic eruption, though? Good. Wow. Good job. Scoria. Same concept, foam. But what's the difference here?
One's darker than the other.
Why is this one darker than the other?
Dark silicon.
Because it's a different magma.
What magma is it?
Basalt.
That's a rock.
Dark silicon.
It's rich in dark silicates, yeah. Which, what do we call that composition? Mafic. Good job. Okay, this comes from a mafic magma. This one comes from a felsic or intermediate magma. But they're essentially the same, okay, in their creation. This one is darker because it has more dark silicates. This one has more silica, okay? This will not float on water, by the way. It has too many dense minerals in it. This one does because it's just made out of glass. Cool? Pumice and scoria. Move these out of your way. Right. Now let's talk about how volcanoes form. What a volcano, how it's designed. We have a surprise visitor. This is my wife, Jessica. I didn't know she was coming. No, you can hang out. Okay, so we're talking about the design of a volcano. So a volcano makes this general cone shape. Why does it form a cone? Well, every time it erupts, it's going to spit stuff out. What are some of the things it spits out? Lava, ash. Yeah, there's the pumice, there's the scoria, there's all the cinders, everything we talked about in an eruption. Well, every time that happens, there's a buildup of material around the general vicinity of the vent that's spitting the stuff out. Every time it does that, it's going to build a bigger and bigger mound around that vent. And that vent is just going to have to keep building through it, cutting through it on its way up until you get this eventual cone shape around the outer surface, the vent. Okay, so this is what we've got. We've got our cone. We've got the conduit coming up from the magma chamber way down deep under there, typically 10 to 15 kilometers deep, although there are some volcanoes where it's very shallow. I'll tell you about some of those later. Yellowstone is one of them, spoilers, okay? So then we've got the crater, which is the opening at the top of the volcano, which holds the vent that is the top of the conduit. Every now and then, you will actually get a sort of side conduit that breaks off of this one, chews its way through the center of the volcano, and then you get what we call a parasitic cone on the side. Same source as that one. It just forms on the side of the volcano, okay? Now, there's something on this, there's something I have on this list, fumaroles, that's not actually marked here. A fumarole is essentially a steam vent. When my volcano is getting ready to erupt, it's getting that magma buildup inside of itself. What's it going to do to the rock around it?
Push it.
It might push it, yeah, a little bit. It might expand a little bit. What else is it doing? It's melting some, but more than that, it's just generally heating the rock around it up. Okay, that heat is being transferred to the rest of the rock around the volcano. Now, there's usually a lot of groundwater, a lot of water in rock. So what's it going to do to that water? Are you done with the snake? You are? Okay. Do you want to hold him?
Yeah.
Okay.
Actually, that's the real reason.
Yeah, sure. Yeah. Came for Diablo, not me. Okay. What's it going to do to that water in the rock? It's going to evaporate it. It's going to steam it up. And that steam has to escape somewhere, and so you get vents, steam vents around the perimeter of your volcano. We call those fumaroles. This is actually one of the ways that we can test if a volcano is actually going to erupt or not. You can test the gas composition of the steam coming out of the fumaroles. And if you get higher rates of sulfur dioxide, sure, yeah. So higher rates of sulfur dioxide, carbon dioxide, all those other gases that typically escape from a volcanic eruption, then we have a pretty good idea, yeah, we're looking at a serious event coming up. So that's one of the ways that we can tell. This is another picture of Mount Fagradalsfjall in Iceland that I showed you the video of earlier. Okay, so you can see the cone shape. Here's the crater that's holding the vent. Here's a flow coming out the side. The conduit from the magma chamber is coming up through the middle of that volcano, right? That lava just got expelled and is making its way down. This is a picture. Look at all the people that are standing that close. I love Iceland. Like, these are people on their lunch break. This volcano is only about a mile and a half from Reykjavik, the capital. So these are people literally on their lunch break just going to watch the volcano erupt. So fun. Huh?
But it looks like, I mean, it's big. Volcano.
You're right. It's a small volcano. There are much, much, much larger ones. Like compared to that picture of Mount St. Helens I showed y'all earlier, right? Or Yellowstone. Yeah, Yellowstone or Tambora that you could fit a city inside of. Yeah. Yeah, it's actually very small, but still impressive, right? And perfect for the scale we're looking at just for an idea of the shape. Okay, so now talking about scale, what a great segue. Thank you, Jackson. Okay. We're going to talk next about the different types of volcanoes, okay? So the three types of volcanoes we're learning about are shield volcano. So that's your big, wide, low angle, low profile volcanoes. This is your Hawaii style of volcano. Then we've got cinder cones, which are your smaller, tinier, but still large compared to us, volcanoes that usually have a very short lifespan. And then you've got your composite cones, also called stratovolcanoes. Those are your Mount St. Helens type style volcanoes, the big explosive ones. Okay? So let's start off with shield volcanoes. Shield volcanoes typically start life as a seamount. Who remembers what a seamount is? A mountain in the sea? Excellent deductive skills. Yes. It's a mountain, a volcano specifically, at the bottom of the ocean. How many of those, you remember I told you we have an estimate for about how many of those things there are? There's a lot. There's somewhere between 1 and 2 million volcanoes at the bottom of the ocean that we can estimate. Why don't we have a better number? Because there's a lot and we haven't explored the whole bottom of the ocean. Okay? But there's a lot of them. We know there's at least 1 million, and we can estimate there's up to 2 million. And every now and then they'll erupt, and we won't know that they're going to erupt because it's impossible to monitor that many of them, which is why last year, that one that exploded next to Tonga, it was Tonga, I was about to say Tahiti. It exploded next to Tonga, and no one knew it was going to happen, and it covered the entire island in ash and shut down their tourism for a while, right? Yeah, that's pretty bad for an island that's main export, their main moneymaker is tourism, right? So monitoring these things is definitely something that we're focusing on a lot in the science, but is not perfect by a long shot yet. Still working on that. Okay, so they start off at the bottom of the ocean as a seamount. There are thousands of feet of ocean between that seamount and the top of where the ocean meets the atmosphere, okay? So after millions and millions and millions and millions of years of eruptions, layer after layer after layer after layer after layer of lava being deposited at the bottom of the ocean and building up on top of itself, eventually, it breaches the top of the ocean. And when it does, you form an island. Classic example of this, Hawaii. Hawaii is a combination of 1, 2, 3, 4, 5 volcanic tubes, all coming from the same magma chamber under the crust. But it spent millions of years building up from the bottom of the Pacific Ocean before it finally reached the top. This is a shield volcano, yeah.
How does it, whenever the lava's coming out of the volcano, how does it not become like the pillow stuff that you were talking about?
It does. A lot of it does. But it keeps erupting and pushing pillow tube out that way, pillow tube out that way. And so if you eventually get this big old layer of basalt at the bottom of the ocean after every eruption, and then another one builds up on top of that, and then another one builds up on top of that. Maybe it's 1 foot of rock this time, 10 feet the next. 6 inches one time, 20 feet the next. However long it takes, eventually it does reach the top and make these islands. Okay? So, shield volcanoes, very wide, very spread out, low angle volcanoes made with mafic magma. Why mafic? Well, because that lava needs to be low viscosity enough that it runs out pretty far before it'll cool off. Right? You following me? Great. Okay. Cinder cones. Cinder cones are the smallest type and the most short-lived. They pop out one moment and then they'll just be dead the next. Okay? They're typically very steep-sided because they are made predominantly out of cinders. Okay, mostly the scoria. Where's that scoria at? You got it in your hands. Perfect. Okay, take the pumice too. Okay, none of you use my pumice for spa anything, right? Okay, good. Thank you. I have to sterilize that. Okay, so this is that scoria I was talking about. Okay, scoria is the main thing that cinder cones will spit out. There's not usually a lava flow associated with it. I have a picture of one that may have a lava flow right here, but that's not normal. Okay? Normally there's no lava, just a bunch of cinders and scoria that get blasted out of a tube. And it makes a very high angle volcanic formation like this. Now, when I say that they can pop up out of nowhere, I'm not lying. In the 40s, 43, I have the date here, okay, in Peracutin, Mexico, there was a rancher who woke up one morning and he went out to go work in his fields, and he heard some rumbling, and he saw that there was kind of a space over there not far from his house that had some steam coming up out of the ground, but he didn't have time to worry about it, so he went out to go work in the far fields that day. Well, over the course of the day, he keeps hearing this thunder, but there's no clouds in the sky, and he's really confused. At the end of the day, he gets home and he finds that where the steam was coming out of the ground before, all of a sudden was a gigantic pit filled with fire. And he goes to his house. There's no one at his house, so he goes into town, takes his truck and goes into town. His family ran away from the house and went into town. And it did not take long at all before his entire property was overwhelmed by a volcano, a cinder cone, a very large one. It grew 330 meters in that 1 year. And it actually overwhelmed that entire town. They had to evacuate the whole town. If you look up pictures of the town now, you can actually find the old chapel, the old church, with a lava flow all the way up the walls from this cinder cone. Now, it died in 52, so this thing only lived for 9 years. It's totally dead now. But it came up and made a microvolcano, essentially, in 1 day, and a bigger one over the course of the year, and then it died 9 years later. So that's kind of the track record for cinder cones, which is why I said here one moment, gone the next, right? Very, very small scale of time, geologically speaking. Which makes them kind of dangerous because you never know where they're going to pop up. There's actually a lot of them not far from us. Have any of you ever flown into the Phoenix, Arizona airport? Yeah? As you're flying into the city, you'll notice that there are a couple of kind of half-moon structures that the city is built around. Big old rock formations that are kind of make half-moon shapes. Those are the remains of cinder cones that they built the city around. Okay? And you can see them pretty clearly as you're flying into the airport. All right? Then we've got composite cones. Did you have a question?
I was going to ask, how do they just pop up out of nowhere?
Good question. So the same way that any other volcano does, there has to be a source of magma. But in this case, the magma is either already too cooled or too small to push anything up to the surface. All it does is transfer heat, essentially. And that heat causes, and gases cause an eruption at the surface. Okay? And then there's not enough substance there for it to last long. So it dies out relatively fast. Think of it as maybe there's a side conduit from a larger magma chamber that makes its way out here but doesn't have enough juice to get a bigger volcano going. Okay? Also can be associated with smaller tectonic activity. All right, so back to composite cones. All right, so we also call these stratovolcanoes, by the way. This is your Mount St. Helens type of eruption, type of volcano here. So the large cone shape that we talked about before, the explosive volcanic eruptions that make them very dangerous. These are the most dangerous type of volcano. They're not the biggest one. Why aren't the biggest ones the most dangerous?
Because we know, because we like view those more, so we know about them.
It's not because of how visible they are, actually. One would think bigger volcano, bigger problem, but that's not actually the case. The case is more people, bigger problem. People have historically built their communities around more composite cones than they have shield volcanoes or cinder cones. Add to that the fact that composite cones are the most explosive type, And those are two factors that don't work very well together. The Cascades mountain range, the Andes in South America, those are all composite cones. More than half of the world population lives on a coastline, and almost any volcano on a coastline is in fact a composite cone. Okay? Like Mount St. Helens, not far from a coastline. Okay? Just a day's drive. Less. Far less, actually. All right. So the Ring of Fire, if you've ever heard the term the Pacific Ring of Fire, I showed you a picture of it actually in our first lecture, where you could see the mountain ranges stretching around the Pacific. Okay? That's what we call the Ring of Fire. A lot of those mountains have been built through volcanic processes. Let's talk about some of the dangers of these composite cones. The first thing is a pyroclastic flow. This is my favorite part of the lecture. This is the when I get to tell you all the ways a volcano can kill you. Yeah, it's a good time. All right, so a pyroclastic flow. These are that first burst of gas that come out. You remember when we popped the cork off of the soda, off of that root beer? What was the first thing that came out?
Yes.
The burst of gas, then the foam and all the substance came after that, but it was gases first because it's the gas that's generating the pressure. So that first burst of gas that comes out of the volcano, it also carries ash with it, okay, like this that I showed you from Helens, right? So that ash and gas is expanding outward extremely quickly. I'm talking hundreds of kilometers an hour if it's fresh and you're next to the volcano, okay? So it's expanding outward, and as it does so, it is immolating, destroying everything in its path, burning it to a crisp, flash frying it, gone. Trees, people, bridges, towns, cars, everything. Okay? Burned to a crisp. This is what destroyed Pompeii. Who brought up Pompeii? You brought up Pompeii. So Pompeii was a city built next to the volcano called Mount Vesuvius in Italy. And in 79 AD, it erupted, and the pyroclastic cloud, this pyroclastic flow, swept through the city of Pompeii and its neighboring city of Herculaneum in the middle of the night. Absolutely destroying everything, instantly flash burning everyone as they slept. Okay? Let me actually show you something real quick. Pull up a picture from Pompeii. Okay. These are actual casts of people from Pompeii as they were killed where they slept. Some of them were just starting to get up, right? Maybe they heard something and they were starting to get out of bed. There are dogs, there are mothers holding children where they slept. Instantly annihilated. So how do we have these casts? Well, you remember what happens when superheated ash falls on the ground? What does it make? Tough. That was close. Yes, it makes this tough. That welded ash fused together around the voids where those bodies used to be. The bodies were burned, instantly flash incinerated, but left a void in their exact same shape in that hot ash. And that ash made a layer of rock. And so in the, I want to say late 1800s, maybe early 1900s, I don't remember exactly, some archaeologists were digging through the city and they found that there were these weird holes in the rock. And they found that if they poured plaster in them and then destroyed the rock around it to remove the cast, they were in the shape of people. That's where all these came from. These are plaster casts of the voids left by the bodies of the people that were burned alive in the pyroclastic flow. So now I'm going to show you this video. This is from an eruption in Japan. This is a pyroclastic flow. They had already evacuated this town. These are volcanologists that were staying to monitor the volcano. Yeah, you better run. Don't worry, he actually got smart and got in the van eventually. Now, that's actually moving pretty slow. By the way, every one of those trees, and eventually when it does reach this town, immediately destroyed. That's a 400 degrees Celsius cloud of gas. Okay? It's gonna absolutely vaporize anything it comes across. The only reason why they got out is because the volcano is actually on the other side of this hill. So this is one of the foothills, and the volcano is over there. It erupted. The cloud had to go down the slope, up this slope, and then down this other one. It had lost some momentum. That's why these guys were able to get out. He was wearing a heat suit. It wouldn't have helped. Okay, that's a pyroclastic cloud. Then we've got lahars. Now, I have a picture here my wife is going to recognize very well. Where is this?
Seattle.
That's Seattle. My wife is from Seattle, by the way. Okay. Yes, you could see Mount Rainier. This is Mount Rainier from her house some days. So, Mount Rainier here is a composite cone. Pretty clear. Large cone shape. Okay. Easy stratovolcano. We're used to that by now. Mount St. Helens. What do you see on Mount Rainier? Snow. Ice. What's one of the things that's going to happen when my volcano is getting ready to erupt and its magma is moving up into the volcano? Huh, what? Cooling? Do you think that the ice is going to cool the volcano, or do you think the volcano is going to melt the ice? Yeah, exactly. It's going to melt the ice. And where does melted ice go? Downhill. What's downhill from the volcano? People. A lot of people, as it turns out. Okay. So as all of that melted ice is making its way downhill, it's going to converge on all of the stream and river systems that are being fed by the glaciers from that volcano. There are several major river systems that are fed by ice from Mount Rainier. And all of that melted water is going to make its way into those river systems, and it's going to flood them. And it's going to fill those river systems with all sorts of mud and trees and debris, and it's going to blast through bridges, and eventually it's going to make its way to a couple of major civilizations. Now, luckily, Seattle, at this point in time, is not in danger from a lahar from Mount Rainier. It's actually built on top of several lahar deposits, but not from recent history, and the geological conditions have changed somewhat, and the course of rivers has changed enough that Seattle itself isn't in any big danger. Tacoma, however, which is the next big city down south, definitely is. Okay? Tacoma has millions of people that live there, and it definitely is in danger from these gigantic mud flows, water flows from Mount Rainier. So what's it going to be filled with? We're talking about dozens of feet tall floods that rip everything apart in its path. Okay, this is a picture of a lahar from South America. Here's the old stream bed. There's a person for scale. Look at the size of the trees that got ripped up by that lahar. And then look at how high up the tree line that lahar was. Okay, this is nothing to mess with. In Nevado del Ruiz in Colombia in 1985, there was a volcano that erupted in the mountain range in the Andes up there. But it wasn't the volcano that killed people. It was the lahar that came downstream that no one expected that killed 25,000 people. Okay? So, again, something to pay attention to. There was a study that I read last year that predicted how many people would be affected if Mount Rainier ever did start erupting and generating lahars. And the number was about, if I remember incorrectly, about 14.5 million people would be affected by lahars on the passage of those lahars down all those river systems on their way to Puget Sound. Okay? That's a lot of people. We ought to look out for those people. And so Mount Rainier is actually one of the most closely monitored volcanoes in the world, not only because of its proximity to populations, but also because it has a unique situation. The magma chamber for Mount Rainier is actually much closer to the surface than for most other volcanoes. It's only about 5 or 6 kilometers deep, which means that we would get way less notice before it went off if that magma started moving up. So there's lots of monitoring stations pointed at it. I lived in a town called Ording for 8 months, which was pretty close to the base of Mount Rainier. And it was built next to one of the rivers that is fed by the glaciers from Mount Rainier. On the first Monday of every month, we would have what is called a lahar drill, which is where the sirens in town go off, and everyone in town is supposed to practice picking up their stuff, getting in their car, picking up their kids from school, and getting out of Dodge. That's 7,000 people that live in this town who have just under 10 minutes to leave town before a lahar would take it out. You know how many people practice on the first Monday of every month? No one. Because 7,000 people know that they're not getting out of Dodge in 10 minutes. So they don't bother. Okay? Nevertheless, they still keep testing the sirens, and they still, ostensibly, people are supposed to be practicing. But they know they won't be able to. There's only 3 ways out of that town. There's a road that goes further down the valley, following the river. Not a good idea, right? If there's a wall of water coming towards you down the river. There's a road that goes up the mountain that people take to get to the ski resorts and everything up there. There are a few towns that are even closer to the volcano that you can take those roads to get to, Electron and whatnot. Yeah, there's a town called Electron out there. Okay. And then there is the one road that goes up and out of the valley, but you have to cross the river to get over it. The only viable way to get away from Lahar is to cross that bridge. And as soon as the Lahar comes down, that bridge is gone. So no one bothers practicing. And yet people still live there. So it falls on scientists to improve our forecasting techniques to try and save lives versus compelling people to live somewhere else, which would take, honestly, a lot more effort and time and cause a lot more controversy. Okay? Any questions about composite cones or their associated threats? You guys want to hear one more? I promised I'd tell you a little bit more about ash. Let me tell you about ash. Do you know what ash is? What you're looking at here is microscopic shards of glass. It's the silica from our magma that gets blasted into the atmosphere when that gas escapes initially. This is micro shards of glass. What happens if you breathe that in? It slices your lungs up from the inside and you drown in your own body fluids. Delightful! Which is why, if you ever see live footage of people around an erupting volcano, they will be holding fabric over their mouths. Even if it doesn't look like there's anything falling, like, it's so hard to tell this is in the air, you always cover your mouth with the finest mesh that you can find, so you don't get massive health issues or death because of ash later on. Little safety tip there for you if any of you find yourselves in the proximity of an erupting volcano. Cool? Cool. Okay. A caldera is a structure that forms when a volcano erupts so explosively that it essentially destroys itself. A powerful eruption will actually cause a caldera in 2 ways. Either it will completely destroy the volcano. So you remember Mount St. Helens? You remember how it looked like half the volcano was gone? Think like that, but more. Okay? It basically destroys the whole volcano and leaves a pit in the ground, a crater more or less, but we call it a caldera. Or the other way is, the eruption is so powerful that it empties enough of the magma chamber underneath of the volcano that the remaining volcano collapses down into the magma chamber and leaves a pit at the surface. Those are the 2 ways you can form a caldera. So there are 2 calderas I want to mention. Yellowstone, which has a caldera 15 kilometers wide. You could fit a city inside of Yellowstone. Okay, that's the size of the volcano. And then right here, this is Crater Lake in Oregon. It's a lake where a volcano once was, because the last time that volcano erupted, it made a boom so big, it left a crater in the ground, which has now filled with water. Okay, so those are called calderas. A fissure eruption follows the same process as a volcanic eruption, except instead of one conduit, one tube that comes up from your magma chamber, it follows some sort of crack in the ground, maybe a pre-existing fault or some other structure, but there's a crack in the ground that allows the magma to come up from the magma chamber. And so you get a long line of eruptions like this instead of one tube that forms a volcano. Okay, so that's called a fissure eruption. And it'll generally make what we refer to as basalt plateaus. Okay, so this magma comes out and it spreads out across a larger area in a more flat structure than instead of making a cone. And these big basalt plateaus are the result. So you can see these are all over India, these are all over Siberia, these are all over Idaho and Montana, if you ever go out there, okay? When I showed you that picture earlier of Mount St. Helens, you may have noticed that there is this cute little baby volcano inside of it now, right? Any of you notice that? No? Yeah, you see it now, right? But you may not have noticed it before. Why is there a cute little baby volcano inside of Mount St. Helens? Say it louder.
So it erupted and then everything came back down and it formed.
Well, nothing really came down. It exploded outward, right? It was a very powerful eruption that came out the slope, okay, instead of out the top like we mentioned. But what made this little baby volcano in there?
Cold rock.
What?
Cold.
Cooled rock? Dig into that more.
Like the lava came up and it cooled eventually.
Just because my volcano erupted, has that completely negated, has that completely removed any of the processes that caused the volcanic eruption in the first place? No. Just like with an earthquake, just because you have one event does not mean that the stresses that made that event won't build up again. As a matter of fact, I guarantee they will. Same as with an earthquake. Okay? So the same processes that caused that eruption in 1980 have continued. Pressure builds. There's a little eruption. Every time there's a little eruption, there's a little bit of magma that comes out, becomes lava and solidifies, building a new cone. Every time the cone gets bigger, until here we are. There's a little baby volcano inside the remains of the old one. Yeah?
Could it rebuild itself back up to how it was before?
And bigger, possibly. Do you know what the tallest volcano in the solar system is? It is on Mars. The tallest volcano in our solar system is Olympus Mons on Mars. It is a volcano twice the height of Mount Everest. Twice the height of Mount Everest. You climb Olympus Mons, you're almost in space. Imagine seeing that sucker light up. That would have been a sight for a geologist to see. Huh? And Elon Musk is trying to live there. Well, Olympus Mons is dead. The whole planet is dead, right? Which is a whole nother problem, right, for living there. But yes, Elon Musk would love to live there. Do you guys remember, I think I mentioned this to you the other day, the issue with trying to go to Mars?
Atmosphere.
Right. There's not enough atmosphere, and the temperature is super cold. Even the hottest day on Mars is well below freezing temperature. You can't live on the surface as it currently stands without some extensive technology improvements. Some stuff better than what we've got now. But also the energy it takes to get there is an issue, right? So Elon Musk just wants to get to Mars so he can be the hero that got us to Mars. That's basically what it comes down to. That's all he cares about. Honestly, it would make more sense to build up infrastructure on the moon and then go from the moon to Mars. Because right now it costs about $200 million to send a spaceship from our planet up into space for any meaningful activity. But you could do it for, gosh, you'd probably only use a couple $1 million in fuel if you launch from the moon to get to Mars. Because think about the energy it takes to break out of our atmosphere. You guys know how rocket booster engines work? You ever seen a rocket lift off? So you've got your main rocket, and then there are those big orange booster engines on the side. Those have so much fuel in them, solid state fuel, by the way. Those have so much fuel in them that you cannot have any technology to turn them off. Once you start that ignition, they go, man. So you light those suckers up, and you're committed. Okay, so you light those engines. It takes that much fuel to break out of Earth's atmosphere. Hundreds of millions of dollars worth of fuel, and once you light it, you can't shut it off, which is why they just break away, and we don't really care about them afterward. Okay, they don't remain as part of the structure. Okay. Interesting fun fact: they also burn from the middle. That's where they put the ignition mechanism, is in the middle. So it's like it's burning from the middle out both ends of the booster rocket. That's beside the point. Just an interesting fact. So yeah, so it takes way less energy to get from the moon to Mars than it does to get from the Earth to anywhere else. So back to my point, Elon wants to get to Mars, but he's kind of ignoring the moon, so I don't think it's going to happen. It's going to take way more resources, and he's not pointing them in the right direction. Yeah. All right, back to volcanoes. A volcanic pipe is what we call a magma chamber or a conduit from a long dead volcano that has weathered and eroded away. All the processes at the surface have broken it down until what's left is the conduit that once fed that magma to the volcano. So here, where this volcanic neck is, there once was a gigantic volcano on top of it. Long gone. Now, this igneous rock in the crystallized conduit, this pipe, is often harder, more durable than the rock that made the volcano, which is why it stayed behind while the rest of the volcano weathered away. So here's a little diagram right here showing that this is what's left. This is Shiprock, New Mexico, by the way. Not that far away. You could go drive to it if you wanted to. Okay. Now, how is volcanism tied to plate tectonics? We've already talked about this in our last lecture. Do you remember the 3 circumstances in which the geothermal gradient allows for the melting of mantle rock? What were the 3 circumstances we talked about? Huh? What about temperature? Huh? Increase the temperature. Bingo. How do we do that? Do you remember the magic word? The word that's almost always the answer to everything? No, not because. Tectonics, guys. How many times have I said this happens because of tectonics, right? It almost always comes down to tectonics one way or another. How does tectonics increase temperature? Friction. You increase friction between 2 plates, you increase temperature. You get melted rock. What's the second way? You got to decrease something for this one. Huh? Speak up, Sonny. I'm an old man. Under the surface. I mean, this is all happening under the surface, brother.
Decrease the pressure.
Decrease the pressure. Bingo. And how do we do that?
I don't know.
Releasing gas.
What's our magic word? Tectonics, guys, right? How does that happen? Well, while we're making friction between 2 plates colliding with each other or scraping past each other for the first one, when 2 plates are separating away from each other, it makes a low pressure zone between them. Boom, bada boom, melted rock, melted magma. There. What's our third way? Ooh, this is the tricky one. What's the third way we get melted rock in the mantle? We introduce something to the equation. What did we introduce? I kind of blew your minds with it. Kinda, but it's associated with something else and it makes a compound. Huh? Water! Good! We introduce water. How do we introduce water to it? Tectonics, right. We have an ocean plate subduct under a continental plate. The ocean plate takes a bunch of water into the mantle with it. That water lowers the melting point of the mantle rock. Mantle rock melts. Blobs of magma come up under the surface. They make those volcanic mountain ranges along our coastlines. Those are the 3 ways that the geothermal gradient and melting point can cross each other and make magma. Okay? That all comes down to tectonics. So right here, this Pacific Ring of Fire, notice where this ring of fire is? It's around the edges of the Pacific Plate, where that plate is interacting with a bunch of other plates. Tectonics. Now, that's not always the case. This is the Ring of Fire, and the vast majority of our volcanoes, especially our composite cones, are around there, but they're not restricted to there. Where's that? That says Kilauea and that says Mauna Loa. Where are those? Yes, it's the middle of the ocean. Do you know what's there?
Island?
Yes, it is. It's a chain of islands. And what are they called? We've talked about them today already.
Hawaii?
It's Hawaii. Yes, that's where Hawaii is. Smack dab in the middle of the Pacific Plate. Why are there volcanoes there? They're not associated with any tectonics. What is it called? That's the question. Anyone want to help out Aaliyah? What's it called? There's a seamount. It started as a seamount, but what's feeding it? That's the question. This is something that I mentioned before called a hotspot. Ah, yes, a hotspot. A hotspot is where you have a blob of convection-lifted mantle magma that rises up in the middle of a plate, not near an edge. Not terribly common, but also not super rare. Hawaii is an example of this, smack dab in the middle of the Pacific Plate. Can anyone think of another volcano in the middle of a plate that could be caused by the same scenario? It's not actually on this map for some weird reason.
Iceland?
No, Iceland actually is right here between two plates. Actually, it's right here between two plates, right there. But good thought. I'll give you a hint. It's right here in the middle of the North American plate. And we've talked about it several times. Huh? No. St. Helens is right there along the coastline. Huh? Yellowstone. Yeah, Yellowstone is right here in the middle of our continent, the North American continent, right there. It's not near a tectonic plate boundary. That massive supervolcano is caused by a hotspot. Okay? Yellowstone, Hawaii, hotspots. These islands, hotspots. But what are all these volcanoes out here? Any ideas?
Like what kind of volcano is it?
No. Why are they there? Why are there a bunch of volcanoes right here in the Mediterranean? Say it louder. Oh, you're learning so good. Yes, it's because of tectonics. Specifically what's happening, Africa is being pushed north into Europe. The Mediterranean Sea is actually closing. It's getting smaller year by year. Eventually, give it 10, 20 million more years, there's going to be no Mediterranean Sea, and Africa will have made a megacontinent with Europe. What will we call that? Eurafrasia? I don't know what we would call that, because Eurasia is this one already, but add Africa to that. If you come up with a good name, let me know. I haven't been able to yet, okay? And then we've got this chain of volcanoes right here, because this is the East African Rift. This piece of Africa, this chunk of Africa, is separating from Africa right now, hence why there are a bunch of volcanoes. So you can see that most of our volcanic activity is tied up with tectonics. Good. Okay? It's a byproduct of tectonics. So we've got our convergent volcanism, where our plates come together and either subduct or crash into each other and make a mountain range. Then we've got our divergent volcanism, which is where they're spreading apart from each other, making those rift systems. And because the plates are so thin at that interaction, the pressure is so low you can get magma. So you get volcanoes that pop up there. Okay? Then we've got that intraplate volcanism, those hot spots, right? Remember our lava lamp. We have our two liquids in the same vessel here. There's a heat source at the bottom. The one liquid interacts with the heat source. As it heats up, what happens to it? It goes up. Why? There's no air. When I heat up a material, I'm adding what? Heat is a form of energy. As I add energy, what are my molecules going to do? Speed up. And as they speed up, what happens to my volume? Increases. My mass stays constant, volume increases, density decreases, buoyancy. Buoyancy causes this material to rise upward. As it cools off, shrinks, becomes denser, falls back down. Heats up, expands, becomes less dense, rises back up. This is what's causing that intraplate volcanism, the hot spots in the middle of my plates, the Yellowstone and Hawaii sort of stuff. Okay? This is what causes it, not the interaction of plates. Okay? All right, so these are just some images that I put in the PowerPoint to help you find locations around the world where all these different scenarios show up. It's showing you the intraplate volcanism in Hawaii. It's showing you the divergent volcanism over in Iceland, all of that. Okay, so this is just a good resource for you to utilize as you write your notes or as you prepare for exams or as you work on it, any of the assignments, okay, where it's relevant. Okay, so the last thing I want to talk about real quick is how we live with volcanoes. Obviously, we have to. It's not like we can get rid of them. Hopefully, people don't continue developing more communities around areas that we know are dangerous, but there are already communities that exist. So we have to monitor these volcanoes to make sure those people can stay safe. There are several ways we can do this. Lasers, for example, can measure the size of a volcano. Is it expanding, like Helen's did that last little bit before it erupted? If it's expanding, we know it's probably filling with magma. Are there any earthquakes? There are tiny little swarms of earthquakes that happen when magma is moving around inside of a volcano. We have seismometers set up around these active volcanoes to measure for that. Temperature. There are satellites that their only mission in space is to watch the most dangerous volcanoes and watch their temperature readings. And if they spike even just half a degree, it sends an alert signal to the USGS or any other agency that is in charge of monitoring all that. Okay? Gas output from the fumaroles at the base of the volcanoes. All of these are ways that we monitor volcanoes to try and save lives as geologists. Specifically, volcanologists. Their job is to do that. Okay? Any questions from today's lecture?
So like for those satellites, does one like scan multiple, or is it just?
Oh yeah. Putting a satellite in space is too expensive to just put it on one volcano. Their mission is to watch multiple targets. Yeah. And it may not only just be for volcanoes. It's just as they pass over a certain volcano, they watch it. And then they're on the other side of the planet. Maybe they have a different mission. But you use the same satellite for as many functions as possible because it's so expensive to put them up there. And the more we put up there, the more cluttered it gets, and the more dangerous it is to put another thing up there. The amount of garbage we have hanging out in our orbit is ridiculous, guys. Like, the early astronauts really had no idea. They drop a screw in space, and all of a sudden it's an object traveling at 400 miles an hour that can put a hole in a spacecraft. And there's so much of that stuff up there. I kid you not, there are chunks of frozen poop up there that would kill astronauts if we didn't know where it was. Oh yeah, actually. What we need is to build some big old net and pick all that stuff up out of orbit. It would simplify space travel a lot more. Any other questions? No?
So, you said Mount St. Helena came up from the side, right?
Yeah.
Is it one of those, what is it called? Like the one where,
A parasitic cone? No. So it wasn't because of a parasitic eruption.
it just randomly did it?
It wasn't random. I'm trying to think of a good example for this. Energy follows the path of least resistance, correct? Yeah? Electricity would rather flow through metal than anything else, which is why it's conductive, part of the reason, okay? Water likes to flow downhill, preferably in a stream valley, right? Things with energy follow paths of least resistance. So if I am increasing pressure inside of a sealed vessel, but there is a part of this vessel that is thinner than the rest, that pressure is most likely going to push out that thinner wall, right? That north slope was thinner than the top of the volcano or the other sides. And because that was the thinnest slope, the pressure blasted out that way instead of out the top.
Why was the top thicker?
It had the most recent buildup of rock from the last eruption. So in a way, that volcano sealed its own fate for where it was going to blow up. Yeah. Anything else? Great. Okay, well, I've already given you all the information that you need for Lab 2. There is a Lab 2 PowerPoint, but it's review from what we talked about last time, so I don't need to go into it last time and this time. It is there for your review, though. Lab 2 is officially assigned. You're still working on Lab 1, totally fine. I get it. Lab 1 is the longest. I get it if it takes a little longer, but you do have Lab 2 assigned at this point. Okay. If you need any replacement trays, if you want me to take away tray 1 for the first lab and give you tray 2, let me know. My online students, feel free to ask any questions in the comments. If you cannot use the comments, you know you can send me an email. And yeah, that's week 2, everyone.